Hello everybody, welcome to chapter 4.2. You guys have already watched a video on 4.2, but I want to give you just another set of examples and we'll do the rest of the problems tomorrow in class. Our objectives are going to be very similar to before. We're going to evaluate an integral using the limit process, and we're also going to evaluate integrals using geometry and properties of integrals. So let's get started. Let's draw a line. And let's begin. So, evaluating using the limit process. As I said before, there are much easier, more intuitive ways to find integrals, but it is important that we know more than one way, and it is important that we understand how to use limits and summations to get there too. So, I'll do one more example of this with you guys. So let's say we are asked to evaluate the integral using limits or using the limit process, and our integral is -2 to 1 of 2x dx. It's important to identify a few different things. First of all, in this particular problem, our delta x, remember we find delta x by doing b minus a over n, b minus a over n, which in this case is 1 minus a -2 over n, which ends up getting us 3 over n. And our c sub i, our book refers to it as c sub i. We can find that by doing the the lower bound, -2, or a, plus delta x times I. When we fill in everything, for this problem, the lower bound a is -2. Then we say plus delta x, well delta x is 3 over n, times I. That means we have -2 plus 3i over n. So, we did practice in class today going from the integral to the summation, or going from the summation to the integral form. Right now we're going to kind of go backwards. We're going to go from the integral to the summation form. So here's how we do that. Again, this step is just rewriting the integral as a limit. And here's how we do that. Move that paper up a little bit. Move this one down. There we go. Rewriting the integral as a limit looks like this. We take the integral, -2 to 1, 2x dx, and we say that's equal to the limit as n approaches infinity for the summation n(i) equals 1 of our function at the c sub I value times delta x. And from this, we can sort of fill in everything else. Remember, f of ci, well, we have to look at what our original f of x was. Our original f of x is going to be 2x. That's the original function that we are given in the inside. So, what we're really going to be doing with the whole f of piece is we're going to say everything else doesn't change. But this piece, the f of ci, we're going to say 2 times the ci. And remember, ci is this whole thing right here that we found earlier, -2 plus 3i over n. So, let me rewrite this bigger. So, that's equal to the limit as n approaches infinity of the summation n(i) equals 1, and remember, f of ci is really 2 times c sub I, which is -2 plus 3i over n, times delta x. And delta x, in our case, was 3 over n. Okay, and from this point onward, you guys, it is just a matter of simplifying and using summation properties to completely simplify, and we'll take the limit as the very, very last thing. So from here, we still have this whole piece. It's not going away, and it takes a long time to say, so I'm just going to write it. That part doesn't change. Over here, however, what we're going to get is negative 4 when we first distribute our 2, right? Distribute our 2 here. Plus 12i over n. And now, next, we're going to take this 3 over n, and we're going to distribute it. And when we do that, again, the first half stays the same. I'm not going to keep saying that out loud because it is lengthy. Okay. Negative 4 times 3 would get me negative 12 over n plus 12i times 3 would get me 36i, and then n times n would get me n squared. Okay. So, what I can do here, oh my goodness, I did my math incorrectly. That is not true. 2 times 3i should get me a 6i, pardon me, 6i, and then here, when I do 3 times 6, I should get 18i on top. My goodness, that was a silly mistake. My bad. So that's 6i, and that's 18i. Okay, great. Now, what I can see when I look at this is that each term in here has a 6 over n that I can factor out. So I can rewrite things. And I'm going to factor out of the summation 6 over n. And when I do that, I'm going to be left with a negative 2 plus a 3i over n, right? Because I had that n squared, so I still have an n there on the bottom. Now is when things get kind of interesting. I can take out my constants, and I can do the summation of each individual thing. So I'm going to be left with everything that's on the outside right now, that's still there. But now I'm going to take the summation of each individual thing. So I'm going to take the summation of negative 2 on the outside of 1. And I'm going to do that because there's a property for the summation of 1 that's going to be really easy for us. And then I'm going to do the summation of 3 over n outside summation of I. Okay, so we took out the constants that were helpful there. And now what I'm going to do is I'm going to recall some things. And I'll show you what I mean. To simplify this piece right here, the summation of 1, remember the summation of 1 is just n. So what I really have going on here is negative 2 times n, or just negative 2n. And then recall that you also have another property you can use here. The summation of I is that n outside n plus 1 over 2. And so I'm going to throw that in here for this piece instead of writing the summation. So I'm going to say plus 3 over n outside all of this stuff. N outside n plus 1 over 2. Okay. Now we're getting somewhere. We're really close. We're going to have to do a bunch of simplifying though. We still have the outside pieces. They didn't go anywhere. We still have 6 over n. And we still have a negative 2n. But now let's start to simplify some things in here. What we can do is just kind of mental math this part. N times n would be n squared, and n times 1 would be n. So what I really have going on here is 3n squared plus 3n over 2n. And what I need to do from there is take my 6 over n on the outside and distribute it in here. When I do that, I'm going to get negative 12n over n, right? 6n times negative 2n is this, negative 12n. Use your parentheses also. And then I'm going to get 6 times 3, which would be 18n squared. And then 6 times 3n would be 18n. And I have that all over 2n squared. And again, that comes from just distributing this to every piece in here. So now what I need to do is simplify right here with my n on top and my n on bottom. And here, I can write this out as two separate fractions. I can write it out as 18n squared over 2n squared plus 18n over 2n squared. And now this is kind of easier to work with. I can see that what I really have going on is n squared over n squared, which goes away, and 18 over 2 should get me 9. And here, n and n cross out, but I still have an n on the bottom, and 18 over 2 becomes 9. So I have a plus a 9 over n. And here I still have a negative 12, and I'm still taking the limit. And that's the last thing I get to do now. When I look at this, I take the limit as n approaches infinity. And remember, whenever something on the bottom of a fraction is approaching infinity and there's a constant on top, that's really just getting close to 0. If I made the bottom of this huge, this would become a really, really, really small, insignificant number. So instead I'm left with these constants here. And negative 12 plus 9 is negative 3, and that is my answer. That is my evaluation of that integral. Let's talk about areas of common geometric figures. Again, right, because you've seen this before, but it doesn't hurt to see things more than once. Okay. Areas of common geometric figures. And we are going to start with the integral from negative 1 to 2 of 7 dx. And then we are going to take the integral from 2 to 5 of 3x minus 6 dx. And we're also going to take the interval from 0 to 4 of 16 minus x squared. Oh, pardon me, radical. Oops, that's a radical there. Radical 16 minus x squared. So let's start here. Here's what would happen if I graphed this. If I graphed the function 7, y equals 7, then I would be looking at 1, 2, 3, 4, 5, 6, 7, a horizontal line at the y value 7. That's this line up here. And then I'm looking at the x values from negative 1. We'll call that guy there. Let's draw a line. To 2. And let's draw another line. There we go. So what I'm interested in is this rectangle here. And I can look at this rectangle and I can tell that its width is 3. To go from negative 1 to 2, that's 3. And to go from 0 to 7, that's 7. So it has a width of 3 and a length of 7. To find the area of a rectangle, I multiply the width times the length equals 21. Right? Area equals width times length. And so 3 times 7 equals 21, and that's the area there. To do this integral here, I need to graph this line. I need to graph this function 3x minus 6. And I can do that if, going to make kind of a really long y-axis here, so you should do the same. And I'm going to start at negative 6. I'm going to go down 1, 2, 3, 4, 5, 6. Make a point. 1, 2, 3, 4, 5, 6. That should be good on my x-axis. And then my y-axis, I'm going to go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We'll call that one 12. Okay, great. So I'm down here at -6, and I have a slope of 3. So I'm going to go up 1, 2, 3, 1, 2, 3 over 1. I'm going to go up 1, 2, 3 over 1. Looks like my x-intercept is happening at +2. And I keep on using my slope to make the rest of my points. I go up 1, 2, 3 over 1, up 1, 2, 3 over 1, up 1, 2, 3 over 1, and once more. Oh, no, I'm good to go there. All right. So now, once I connect those points, I can take a look at my boundaries. I'm interested from 2, just going to draw a little dashed line where my boundaries are, to 5. And 5 is right here, that last point that we made. And so I can see that the area I'm looking for is this triangle right here. I can recall that the area of a triangle is 1/2 the base times the height. So in our case, that's 1/2 times the base, which is 3, and the height is, remember we went up 3 for every one of these points we made, so we went up 3, 6, 9. And what we can tell from here then is that we would get 27 over 2, and that would be our area. For this integral here, what we're going to be doing, let me zoom in maybe just a little bit closer. There we go. Okay. For this integral here, it's important that you recognize that this is a half circle. When y equals this radical, we actually have a half circle, and we have a half circle with the radius of 4, centered at the origin. And so I go out 1, 2, 3, 4, go out 1, 2, 3, 4, and go up 1, 2, 3, 4, right? Because the circle is centered around the origin. And I go up and over to my other side, and I stop. And so I'm interested in the area of this half circle here. Remember that the area of a circle is pi r squared. But we're not interested in the whole circle. We only want half, so we're going to multiply this by 1/2. And so for us, we still have pi. Our radius is 4. 4 squared is 16. And so I get 16 times 1/2. I get 8, and then pi, and that's it. That's my area. That's my integral there. Okay. Another topic I'd like to go over with you in this video is absolute value and the additive interval property. Absolute value functions and the additive interval property. Okay. I guess I'll underline that part too. There we go. Alrighty. What I would like to do an example of is to evaluate the integral from -5 to 0 of the absolute value of x plus 3 dx. And in order to get us started with this, I want to review some properties of absolute value functions with you guys that might not be so fresh. Let me use a separate sheet of paper to start you off with that. All right. So what I want you to understand about absolute value functions is if we have like an f of x equals, I'm not sure, absolute value x plus 1, the graph of this, oh goodness gracious, pardon me, let's use a coordinate plane that's straight, not a diagonal line. Whew. means that I have a vertex at -1, right? Because we remember shifting transformations. If I have a plus next to an x, I actually go to the left one, or left however many there are in here. So I'd go left one, that's my vertex. And then I have a slope of whatever's next to x. There's a 1 in front of x here, so I have a slope of 1. That means I'm going to go up 1 over 1, up 1 over 1, up 1 over 1. And in the other direction, I'm going to go up 1, over 1, up 1, up 1 over 1, and then up 1 over 1. And my absolute value function is going to do that classic little triangle thing that it always does, and it's going to have that vertex at 1. Notice that, let's use another color here, this half of my absolute value function has a positive slope, and this half of my absolute value function has a negative slope. So this half is represented by the function -x minus 1, and this half of the function is represented by this half of the graph is represented by the function x plus 1. So for our graph, for when we're looking at the absolute value of x plus 3, to help us with the integral, we should graph it first. And I guess I'll do the whole integral piece here too. So to go from -5 to 0, x plus 3 dx, we're going to graph it, and we're going to make that vertex happen at -3. Okay. 1, 2, 3, 4, 5. Guess we'll do 6 over there also. We'll call this -3 here. That's where we know our vertex is going to be. Similar as before, our slope in front of x is going to be a 1, and so we're going to go up 1 over 1 in both directions. Up 1 over 1, and then I'm going to go up 1 over 1 once more, up 1 over 1, and I can see the triangle starting to take shape. And over here, I'm going to go backwards. I'm going to go up 1 over 1, up 1 over 1, up 1 over 1. And then I have my absolute value function. Remember, just as before, this is kind of split into two pieces. I have a triangle here from the bounds of 0 to -3, and I have a triangle here from the bound -3 to -5, right? Because that's where I was stopping, was at -5. Okay. Ignore this one in the middle, that shouldn't be there, pardon me. What I want you to see is the fact that we have two triangles going on here. And these two triangles have different bases and heights, but remember, the area of a triangle is just 1/2 BH. So the base of this first one over here to the right is 3, and the height is also 3. So we can find the area to be 9/2, because 3 times 3 times 1 is 9, and we have that over 2. The area of the next triangle over here is, what do we have? A base of 2, a height of 2, and we multiply that by 1/2, and I'm going to leave it as a fraction for now. 2 times 2 is 4, and then we'd have 4 over 2. Now what we need to do is look at the area for this entire interval from 0 to -5. That means I have to add the area of this triangle and the area of this triangle together. So I need to add my 4/2 plus my 9/2. And I get 13 over 2. When we think about this as an integral, I want you guys to remember that this side of the function is represented by the function x plus 3, and that this side of the function with the negative slope is represented as -x minus 3. So, as an integral, here's what this looks like. Really, what we can do is use the additive property, and we can say from the bound from negative 5 to negative 3, we're taking the integral of the negative function of negative x minus 3 dx, and we're adding that to the integral from negative 3 to 0 of the positive function of x plus 3 dx. And we already evaluated what those values actually are. We found that this area was in fact 4 over 2, right? This smaller triangle was 4 over 2. And we found that the area here was 9 over 2. And so we come to the same conclusion either way. This one just kind of uses more visuals, but this is how we connect it back to integrals, using that additive interval property. Okay. Let's see. Let's do one more example. Again, let's focus on using the integral properties. So, say we were asked to evaluate the integral from 2 to 4 of x cubed minus 3x plus 7 dx using the following values. That from 2 to 4 x cubed dx is 60. From 2 to 4 x dx is 6. And from 2 to 4 dx equals 2. It's going to be helpful if we realize that this is the same as saying from 2 to 4, 1 dx equals 2. Those two are equivalent statements. All right. And here's how we can use these things to help us. We can rewrite this big integral into pieces. So we can say the integral from 2 to 4 of x cubed minus 3 outside the integral 2 to 4 of x plus the integral of 2 to 4 of 7. And again, I know there should be a little dx after each thing. Pardon me for not writing that in there. Little dx, dx, dx. Okay. And we can evaluate that now using the given information. We know this one was given to us. It was just 60. So we're going to say 60. And now we're doing 3 times the integral of just the x. The integral of the x is 6. So 3 times 6 is 18. So we say minus 18. And then here, we know the integral of 1 is 2. And here we're trying to take the integral of 7. So we can kind of use our constant rule. We can take out the 7 and take the integral of 1 dx. And we know the integral of 1 dx is 2, so we're really doing 7 times 2 here. And 7 times 2 is 14. When I add all these numbers together, I get 56. I guess I should throw some equal signs in there as well. Pardon me. And there we have it. That is all I have to show you. We'll see you in class tomorrow.